All right, welcome. Mr. Richardson here with Unit 13, Thermochemistry. All right, so our first slide here just really has a lot of definitions. Make sure you look them over and have a decent understanding of what the terms are and how we're going to use them this chapter. So the first one is energy. We symbolize it with the capital letter E there, and that's the ability to do work or produce heat. Again, generally in this chapter, we'll be looking at the producing of heat, thermochemistry. Thermo means heat. So quick review. The law of conservation of energy states that anything, chemical reactions, physical process, anything, energy can be converted from one form to another, but it can never be gained or lost. It can never be created nor destroyed. And that'll be pretty important for our calculations in this chapter, is that we always know the energy we're starting with should be the exact same as the energy that we end with. All right, the next term we have is heat, which we symbolize as letter Q. I'm not sure exactly why, but there we are, heat with the letter Q. And this is a measure of the energy that flows from one object to another. And it's always from the warmer object to the cooler object. That's the direction heat always flows. Cold does not flow, warmth flows into a colder object. So when a warmer object loses energy, its temperature decreases. When the cooler object absorbs energy, its temperature rises. Hopefully that's pretty straightforward. So next we have two terms here. Make sure you look these two terms over and have a good understanding of them. Heat capacity is the amount of heat needed to raise the temperature of an object by 1 degree Celsius. And that's opposed to specific heat, which we use a little c to symbolize. And this is the one we're going to work with most often. And specific heat is the amount of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius. So when we look at the two differences here, heat capacity could be different for the same material. I could have two pieces of iron. If they are different masses, they're different sizes, then one of them is going to have a larger heat capacity. It would take more energy, more heat, to raise a larger object by 1 degree Celsius than a smaller one. Whereas specific heat, lowercase c, that deals with how much per gram of the object. So if you're working with iron is going to have the same specific heat. A large piece, a small piece, doesn't matter. Iron will have the same specific heat. Finally, calorimetry is a process of measuring heat changes. And it's actually a very old process. Scientists have been using this for hundreds of years. We'll usually take 2 styrofoam cups or a calorimetry. I think you used the calorimetry cup last chapter a little bit. But they're basically styrofoam cups, and styrofoam's a very good insulator. So in theory, all the heat transfers that happen within this system here are going to stay constant. So the heat lost by one object will be the heat gained by another object. And you'll see we oftentimes use water. Very easy to measure and calculate the energy lost or gained by water. So that makes it a very excellent tool to use in a calorimetry cup. All right, next up we have endothermic versus exothermic reactions. So on the left side here, I've got an endothermic reaction. Here's the graph. So here's our starting amount of energy. The reaction happens, and then you'll notice the ending amount of energy, the energy of the products, is higher than the starting amount. That's an endothermic reaction. They absorb energy. So that much energy went into the system. These types of reactions feel cold to the touch. So if you feel a test tube that had an endothermic reaction in it, it would probably feel cold to the touch. The heat change, which we symbolize as delta H, triangle is delta, H is enthalpy, which is our heat change. This is going to be positive. I know it seems like, if you're, ending up with more energy than what you put in, it's going to be a positive, a gain of energy. Energy is a reactant. In a couple of days, we'll be doing a lesson where we work with energy or heat stoic. And always remember that a positive delta H, an endothermic reaction, energy belongs on the left side of the equation. It is a reactant. Activation energy is almost always required for an endothermic reaction. You have to put some energy in and keep that reaction going. It wouldn't work to have an endothermic reaction occurring spontaneously, just forever, never, never. You're losing energy. So generally these are not spontaneous. Over here on the right, we have an exothermic reaction. Again, you'll notice here the starting amount of energy. We go through the reaction and we end up with a release of energy. Our products have less energy than what we started with. And that's the telltale sign of an exothermic reaction. These will feel warm to the touch. The heat change, or delta H, is going to be negative. The energy is coming out of the system. It's being lost by the system. Over here, on an endothermic reaction, the energy was going into the system. It's added, so it's a positive delta H. But in an exothermic reaction, the delta H is negative. The energy is leaving the system. Again, when we write those thermochemical equations, energy is a product. It'd be on the right side. It would come out of the equation. Activation energy is usually not required, but it depends on which reaction you're working with. So sometimes there are some exothermic reactions. They have to constantly add energy to keep them going. But usually you don't need an activation energy. The energy released will go ahead and start the process all over again, and the reaction will run to completion. That's what we call a spontaneous reaction. And once you get it started, think of a piece of paper and lighting it on fire, perhaps. That would be a very exothermic reaction. Yes, you'd have to apply the spark, but once you get that first little bit of paper lit, the energy that's released will go ahead and start the next part of the paper burning, which will in turn release energy to start the next part, and that's a spontaneous reaction. All right, we have several units of energy. First of all, calorie. Notice a capital C. This is a dietary calorie. So these are the ones you've heard of, you've probably talked about with friends. In chemistry, we use lowercase calorie. So a calorie, lowercase calorie, is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. The dietary calories that we always hear about and see listed on food is really a kilocalorie. We should be familiar with the term kilo. We've seen that quite often. It means 1,000 little calories. They're scientific calories. In chemistry, we'll usually be using the energy unit joule, which is a J, symbolized by J. So some conversions you'll need to be familiar with. Again, we just mentioned it. 1 capital cal is really 1 kilocal, which is 1,000 calories. That's infinite significant digits. And 1.000 calories is equal to 4.184 joules. That one does not have infinite significant digits. There are 4 digits on both 1 calorie and 4.184 joules. So the specific heat of water, we have to think again. Specific heat is the amount of energy needed to raise 1 gram of substance by 1 degree Celsius. Well, look at that. A calorie is raising 1 gram of water by 1 degree Celsius, and it takes 4.184 joules to do that. So, specific heat of water is 4.184 joules, or 1 calorie. But again, we'll most often use the unit joules. Let's take a look at some examples. So again, with calorimetry, we can put an object into a styrofoam cup filled with water. Because we know the specific heat of water, if we measure the temperature change of the water, we can determine that that must be the amount of energy or heat that was lost by the other object, the object that we placed into the water. Here is a formula. Again, Q for heat is equal to our specific heat times our mass times our change in temperature. Again, the triangle, delta, stands for change. Take a quick look at our units here. Heat is measured in joules. Specific heat is how much energy per gram degree Celsius. Mass, of course, is grams, and delta T is a change in temperature. So we're looking at degree Celsius. So again, the idea is energy is never created nor destroyed. So the amount of energy that is lost by whatever you're placing into the metal must be the same as the amount of energy gained by the water. And we have a formula there. Heat lost is equal to heat gained. Again, Q is heat, so we can say the Q of one object, Q lost, is going to be equal to the Q gained, which means we can break down that formula to the specific heat of water times the mass of water times your change in temperature of water will be equal to the specific heat of the object times the mass of the object times the change in temperature of the object. And notice I've got the negative symbol, gained and lost. These two energies should be equal but opposite. Let's take a look at some examples. So the label on a can of soda indicates that it contains 150 calories. Notice the capital C. How many joules is this? All right, well, have to know our conversions real quick. So 150 capital C calories is 1,000 little calories. And 1 little calorie is 4.184 joules. So we crunch our numbers. 150 times 1,000 times 4.184. We get 630,000 joules. A joule is actually a very small amount of energy. All right, let's take a look at a specific heat type of problem. When 435 joules, that's an energy, of heat are added to 3.4 grams of olive oil at 21 degrees Celsius, the temperature increases to 85 degrees Celsius. And they ask, what is the specific heat of the olive oil? Okay, well, Q is energy is equal to our specific heat of oil times our mass of oil times our change of temperature of oil. I don't require you to list out your variables as I'm doing, but I'm going to let you know it really does help. So they're telling us we have 435 joules, there's our energy. We know our mass, 3.4 grams of olive oil. And our change in temperature, again, notice it's a change of temperature. It's not one temperature or the other, it's the difference between them. And yes, there are times when you should have a negative change in temperature. So 85 degrees is what we ended at. It's always T final minus T initial. So 85 degrees Celsius minus 21 degrees Celsius. And I got a change in temperature of 64 degrees Celsius. And we're looking for the specific heat, or C, of the olive oil. I'm going to isolate my variable. So again, here is the straightforward equation. Here I have isolated my variable. In order to get the specific heat on the side by itself, I'm going to divide my energy by the mass times the change in temperature. I can plug in my variables, and I get a specific heat of, with significant figures, 2.0 joules per gram degree Celsius for the oil. One more example. Here's a calorimetry example. So what is the final temperature of a 16.4 gram piece of iron when it is heated to 100 degrees Celsius and then dropped into 114 milliliters of water at 15 degrees Celsius? We've got quite a bit going on here. Again, I highly recommend that you list out the variables you have, otherwise it can get quite confusing. So again, our formula is going to be the energy of the water is equal to the energy lost by the metal. We know the specific heat of water, 4.184 joules per gram degree Celsius. The mass of water, they told us, is 114 grams. Well, they told us 114 milliliters, but hopefully At this point in the year, we're all familiar with 1 gram of water is equal to 1 milliliter water, the density of water. And the change in temperature of the water is our final temperature, which we don't know what it is. That's actually what the question's asking. Minus 15 degrees Celsius. That's where we started, our initial temperature. The other variables that we have, they gave us the specific heat of metal, so 0.4494 joules per gram degree Celsius. The mass of the metal was a 16.4 gram piece. And the change in temperature, that piece of metal started off at 100 degrees Celsius, and it ended at, hey, there's our TF again, our final temperature. Now the idea is that the temperature, the final temperature of both the water and the metal should be the same. If you put a hot piece of metal into cold water, they eventually will equalize. The metal will lose energy, the water will gain energy, and eventually you're going to have a piece of metal that is at the same temperature as the water. And that's what we're trying to show here. So our equation, notice I've substituted in for the delta T's, TF minus TI. It's always final temperature minus initial temperature. Okay, plug in our variables. So simplify by multiplying and distributing. Combine your like terms, watch your units. And solve. Our final temperature should be 16.3 degrees Celsius for both the metal and the water. And that was a particularly difficult question, finding the final temperature where you have a variable, an unknown variable on both sides. More often than not, you're going to be asked to find the mass of the metal or the specific heat of the metal. Just one variable and not the TF on both sides. So hopefully this helps. You've got some homework. Here it is, due Wednesday, February 20th.